Okay, let's take a look at example 4, where we're finding the current in a circuit by solving a separable equation. In section 2, we modeled the current I of t in the electric circuit shown in figure 5 by the differential equation. We had L times di divided by dt plus R times I, which is equal to E of t. And what we want to do is we want to find an expression for the current in a circuit where the resistance is 12 ohms, the inductance is 4 henries, a battery gives a constant voltage of 60 volts, and the switch is turned on when t is equal to 0. What is the limiting value of the current? Now, we had L, which is equal to 4. We know that R is equal to 12, and that E of t is equal to 60. And that equation would become the following. We would have 4 times di over dt plus 12i, which is equal to 60. Or if we simplified it further, we would get di over dt, which is equal to 15 minus 3i. And the initial value problem is the following. We would have di over dt, which is equal to 15 minus 3i, or we have I of 0, which is equal to 0. Now, we can recognize this equation right here as being separable, and we can solve it as follows. We can divide both sides by 15 minus 3i, and then we can bring and multiply both sides by dt, as long as 15 minus 3i does not equal 0. So now we're going to end up with 1 over 15 minus 3i di, which is equal to the integral of dt. So taking the antiderivative of this, we would get negative 1/3 times the natural log of 15 minus 3i equals t plus c. Now we can rewrite this in terms of a logarithm. So writing this in terms of a logarithm, before we do that, what they're doing here to get to this step is multiplying everything by negative 3. So we're going to get the natural log of 15 minus 3i, and that's going to equal negative 3 times t plus c. And then they're going to rewrite it in terms of a logarithm, so therefore it would be 15 minus 3i is going to equal e to the negative 3t plus c. And so now, since we have the absolute value, we can then separate this using our properties of exponents. So we're going to have e to the negative 3c times e to the negative 3t. And remember that this is plus or minus if we're taking away the absolute value. So we can rewrite a to be equal to plus or minus e to the negative 3c. So we're going to get 15 minus 3i, which is equal to a e to the negative 3t. And then solving for I, then we can subtract 15 to both sides, and then divide everything by 3. So I is going to equal 5 minus 1/3 a e to the negative 3t. Now, since our initial value problem had given us an ordered pair where we have 0, 0, if we plug in 0 for t and 0 for I, then we would get 5 minus 1 over 3a, which is equal to 0. Solving for a in that equation, by subtracting 5 and multiplying both sides by negative 3, a is going to equal 15. And so therefore, the solution to this problem would then be I of t, which is equal to 5 minus 15 divided by 3, which is 5, e to the negative 3t. And so the limiting current in amperes is the following. So as the limit as t approaches infinity of I of t, which is equal to the limit of t as it approaches infinity of 5 minus 5e to the negative 3t, which is equal to 5 minus 5 times the limit as t approaches infinity of e to the negative 3t. And we know it's going to give us 0. So 5 minus 0 is going to equal 5. And what that tells us is, if you look at figure 6, it's going to show how the solution in this example, which is the current, approaches its limiting value. And so comparison with figure 11 in section 7.2, it shows that we were able to draw a fairly accurate solution curve with the direction field. So again, here is your horizontal line, and then there is your curve.